Hello, this video is on chapter 9, sections 9.3 to 9.5. This is about acid, base, and strengths first. I want you to take out your yellow packet of reference and go to page 5 of that yellow packet. And the page 5 is all dedicated to acid and bases. And so I have this page open. So there is a table there with a list of acids, and if you look at their formulas, they are made of hydrogens, halogens, sulfur, nitrogen, oxygen, phosphorus, carbon, which are all non-metals. And so acids are covalent compounds because they are made of non-metals only. However, they behave like if they are they behave like ions in solution. For example, HCl, when you place it in water, it dissociates into H3O plus and Cl minus. And so remember how an acid-base reaction is having an acid that donates a proton. So HCl here is the acid. It will donate a proton to the water, and water will act as a base. So when the proton leaves HCl, it leaves behind Cl minus, right? The negative charge comes from the fact that HCl donates an H plus. The H plus goes with the water and forms the H3O plus ion, the hydronium ion, right? When you add H plus to this formula, it becomes H3, and the positive charge from the proton gets into the H3O plus. So HCl is a strong acid, which means it's a strong electrolyte. If you remember what a strong electrolyte, it means that it completely dissociates into water into ions. So when you place HCl in water, it completely dissociates into H3O plus and Cl minus. And this is shown by the single arrow going from left to right. There's no other arrow going backward. And that arrow, single arrow pointing to the right, is indicating a complete reaction. And that's what happens when you have a strong electrolyte. It completely dissociates into ions and then can conduct electricity strongly. And if you look at the modeling here that is representing HCl to the left, you see the chloride ion. It's the big green balls, and then you have water, and water is in the background, and then the molecules you see with the oxygen and the 3 hydrogens are the hydronium ion, and they float around with the chloride ions, and there is no HCl molecule anymore. It's all completely dissociated. In opposition, a weak acid is a weak electrolyte. A weak acid like CH3COOH, this is the acetic acid here. That's a weak acid, and when you place it in water, it dissociates into H3O plus and the acetate ion. Because the acetic acid, when it donates a proton, H plus, goes with H2O, and H plus plus H2O makes the hydronium ion, H3O plus. And then the acetic acid, when it loses its H plus, it becomes the acetate ion. So acetic acid is a weak acid because it's a weak electrolyte. And if you remember what a weak electrolyte is, it's a molecule when dissolved in water that only dissociate partially in water and make a small amount of ions. Here, only a small fraction of this acetic acid is making the acetate ion and the hydronium ion. So you have few ions, and the proportion of acetic acid is still very large. And because it's neutral, it's a neutral molecule, it cannot conduct electricity. And that's why it's weakly conducting electricity, because there's few ions in solution. If you look at the model here on the right, you see a lot of acetic acid molecules, and then there is only 2 acetate ions and 2 hydronium ions. And so out of a total of 11 molecules shown here, you have 4 ions over 11 particles, which shows that you cannot conduct electricity strongly because the proportion of ions is small. And that's what a weak acid is. And the key to recognize a strong acid versus a weak acid is in the arrows of the chemical equation. For a weak acid, you have a double arrow, an arrow that shows it dissociates, and a reverse arrow that shows that it stays as an acid in water and it is not dissociated. And so that double arrow tells you it's an equilibrium and you still have a lot of acid not dissociated. It's the same principle for bases. A strong base is a strong electrolyte. In water, 100% of the base will dissociate into ions. So for the bases, you need to know that all strong bases will have the hydroxide ion in their formula. For example, NaOH, there is the Na plus ion and the OH minus ion. The OH minus ion is called the hydroxide ion, and any ionic compound made of the hydroxide ion and an alkali metal or an alkaline earth metal will make a basic compound, a base. And the reason why those alkali metal and alkaline earth metals are called like that, it's precisely because they make compounds that are basic. Know that basic is synonymous to alkaline, when the word alkaline means it's basic. So the alkali metal and alkaline earth metals are making basic compound, especially even strong bases if they are associated with the hydroxide ion. Anyway, so when NaOH, which is a solid because it's an ionic compound, typically they are solid in by themselves. When you place it in water, it will dissociate into Na plus and then the hydroxide ion, OH minus. And notice here the arrow is arrow going to the right, and there is only one arrow. So it's a complete dissociation into ions. And that's why it's a strong electrolyte, because now it's only a mixture of ions that can carry the electricity. And if you look at the model on the left here, you see the gray balls represent Na plus and then the OH minus, and that's only what you see. There is no NaOH. So that's a strong base. Now a weak base is a weak electrolyte, and that means only a small fraction of the base will dissociate into ions. The example here is ammonia. Ammonia by itself is a gas. When you place it in water, it will dissociate into the ammonium ion and the hydroxide ion. Because ammonia is a base, it will accept the proton from water. And when it accepts a proton, it becomes NH4 plus. And water will act as an acid in this case and donate its proton. And when H2O loses an H plus, it becomes OH minus, right? You can see that if you add H plus and OH minus together, the positive and negative charge cancel, and then you have H2O. So here again, the key to recognize a weak electrolyte is the double arrow that shows that it's an equilibrium, it's not a complete reaction. And so the bottom arrow going backward shows that this side is even happening more strongly. So it's only really a small fraction of the base that dissociate into ions. And that's why it's a weak electrolyte, because it's only a small proportion of ions, and a large proportion of the NH3 is not, it's a neutral molecule, so it's not able to conduct electricity. If you look at the model on the right side here, you can see it's mainly NH3 molecules, and then you have 2 OH minus and 2 H3O plus only. So these ions will carry the electricity, but they are too few, so they will weakly conduct the electricity. This table is in your yellow packet. It's the same table. On the left side, it lists the acid, and on the right side, it's their conjugate base. So if you want to see conjugate acid-base pair, you read a row. And for example, hydroiodic acid, HI, its conjugate base is the I minus ion, which is the iodide ion, right? So the only difference between the acid and its conjugate base is an H plus, right? The acid has the H plus included in its formula, and the conjugate base doesn't have the H plus in its formula. And so if you look on the left side here, you can see that the acidity is increasing from bottom to top, which means that on the top of the list are the strong acid. And then as you go under the hydronium ion, it's the weak acids. And so there is only a few strong acids: hydroiodic acid, HI, hydrobromic acid, HBr, hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, and the hydronium ion, H3O+, which has water as its conjugate base. When you look below that, all the other acids are weak. Phosphoric acid, hydrofluoric acid, acetic acid, carbonic acid, the ammonium ion, hydrocyanic acid, and water is a very weak acid. Notice how hydrofluoric, HF is the only halogen that makes a weak acid. All the other halogens are making strong acids like HI, HBr, HCl. And so on the conjugate base side, there is only one strong base, and it's the hydroxide ion. So it doesn't clearly say that on this table, but all the others are considered weak bases. And the hydroxide ion is the only strong base. Of course, it's not found by itself. In general, it's associated with the alkali metal, like Li, lithium, sodium, potassium, rubidium, cesium, and francium. And then it's also associated with the alkaline earth metals like beryllium, magnesium, calcium, strontium, barium, and radium. And so all of these will make strong bases because they are associated with the hydroxide ion. So this is part of your practice problems. If you have the practice problems paper with you, it's practice problem number 5, number 5. So you can pause and listen to the rest once you have tried to solve the problem by yourself. So identify each of the following as a strong or weak acid or base. So you need to decide first if it's an acid or a base, and then if it's a strong or a weak acid or base. So HBr is a strong acid. It's an acid because it has an H as a first in the formula. And if you look at the table, page 5 of the yellow packet, you will see that HBr is listed there as a strong acid. HCN, that's the hydrocyanic acid, is listed in your table as a weak acid. We know it's an acid because it has H as first element in the formula. NaOH. NaOH, there is no H as first in the formula, so it's a base. And you need to recognize here that there is the OH minus ion, the hydroxide ion. And the hydroxide ion, I just said, is the strongest base and the only strong base. So NaOH, sodium hydroxide, is a strong base. H2SO4. H2SO4 is having hydrogens first in its formula, so it's an acid. And if you look in the table, it's listed as a strong acid. Cl minus. Cl minus is the chloride ion. Do you see an H there? No. So Cl minus cannot be an acid. It's a base. And if you look in the table, it's a weak base. It's the conjugate base of HCl. HCl is a strong acid. And typically when you have a strong acid, the base will be weak. And vice versa, when you have a strong base like OH minus, its conjugate acid will be weak because the base is strong. And the conjugate acid of OH minus is H2O, and H2O is definitely a weak acid because it's also considered a weak base. It can act as both. And maybe you remember that we call this substance amphoteric when they can be both an acid and a base. So we'll move on to writing equilibrium constant, and that's another way to find out if you have a weak or a strong acid. It's by calculating the equilibrium constant. And when you have an equilibrium constant for an acid-base reaction, or an acid dissociation reaction, we call that an acid dissociation constant. So let's look at the generic reaction of an acid when placed in water. HA is a gas. When placed in water, will be in equilibrium with the hydronium ion and A minus, the A minus ion. How we get this? It's because HA is the acid in this case, because it has that H first in the formula. So it will donate its proton to the water. When HA donates its proton to the water, you add H plus to H2O, and that becomes H3O plus. And HA without its H plus becomes A minus. The bond between HA becomes a lone pair, and then H plus leaves with a positive charge, so it leaves behind a negative charge. So we will write the equilibrium constant for this reaction. Remember, equilibrium constant are a concept we encountered in chapter 6. And so if you want to be reminded of the formula you need to use for that, go to page 1 of your yellow packet. In about the middle of the page to the left, you will see equilibrium constant. Kc equals concentration of product over concentration of reactant. Remember those brackets, squared brackets, mean concentration. So here we will write the Ka because it's an acid dissociation constant in this case, because this is an acid dissociation reaction. So we need the concentration of the product on top. So here product are on the right as always, and we will take H3O plus in brackets times the A minus in brackets. There is no exponent because the coefficient in front of H3O plus and A minus are 1. So you multiply them together and there is no exponent. Over, and then the concentration of the reactant goes under, and the reactant in this case is HA and H2O. However, you need to remember that we do not include liquids and solids in equilibrium constant. Their concentration is considered constant, and so it's not included in there. So in this case, it would be just the concentration of HA on the numerator. And again, HA has a coefficient of 1, so there is no exponent on that concentration. So as I said, this is called the acid dissociation constant, Ka. So we have the A in subscript to recall that it's an acid dissociation constant. And there are many values of Ka that you can find in tables, in chemistry dictionaries, if you will. Chemists have done experiments and calculated those values for each acid, because each acid has a Ka value and they are different for all of them. So now if we look at this expression, on top we have the product, and if we have a strong acid, it's an acid that completely dissociates. So you could say that the bottom arrow is not there and it's a complete reaction going from left to right. So you would have very large concentration of H3O plus and A minus, right? So the numerator of this equilibrium constant would be a large value. And in the denominator, the concentration of HA would be small because all of it is completely dissociated into the ions to the right. So that means our Ka has a large numerator and a small denominator, which means when you calculate Ka, it will be a very large value. And so this confirms that the stronger the acid, the larger the Ka value. That's how you can tell, you know, if you have a strong acid or a weak acid. It's looking at its Ka value. And the larger it's, the stronger is the acid. It works the same way with bases. And so that's a generic reaction for the dissociation of a base. So when you place the base in water, the base is symbolized by B and its lone pair. When placed in water, it dissociates into OH minus and BH plus. How we So our base B with the lone pair is a proton acceptor. And so that lone pair will bind to the H plus and accept it. And so when B binds to H plus, it becomes BH plus because the H plus comes with a positive charge. And water here is acting as an acid and donated an H plus. So when you remove H plus from H2O, you have only one H left, and H plus leaves with a positive charge, and so it leaves behind a negative charge. And so you get OH minus. Again, you can verify that this is correct, because if you add H plus to OH minus, the plus and minus cancel, and you have two H's and one oxygen, which is water. So let's write the equilibrium constant for that reaction. Again, we need K. K is the concentration of the product over the concentration of the reactant. So on the right side, we have the product, and here we have OH minus times BH plus. Remember how these brackets means concentration in molarity. So it's the concentration of OH minus times the concentration of BH plus. There is no exponent because their coefficients are 1, over And again, this time the reactant is only B with its lone pair, because the water cannot be included in the equilibrium constant because it's a liquid. This is called the base dissociation constant, Kb, because it corresponds to the reaction of the dissociation of the base. And again, the stronger the base, the larger the Kb value. If we look at this formula again, you can see that if the product have a large concentration, which means the hydroxide ion and the BH plus ion, if they are in large concentration, the numerator will be a large value. Over the denominator, and if you have a strong base, the denominator, the base will be completely dissociated into its ions. So the concentration of the base will be very small. So a large numerator over a small denominator will result in a large Kb value. And so that confirms that the stronger the base, the larger the Kb value. So this is practice problem number 6 in your list of practice problems found in chapter 9. So again, I will let you pause now so that you can do that on your own before looking at the answers. So what is the acid dissociation constant for the following reaction? If the equilibrium concentrations of product and reactant are the following. So you're given concentrations of HCN, Cn minus, and H3O plus. The equilibrium equation is given there. HCN, hydrocyanic acid, when placed in water, will dissociate into the cyanide ion, Cn minus. And so that's because HCN donates its proton to water. So HCN minus the H plus becomes Cn minus. And then H2O accepts the proton as a base and becomes H3O plus. So first we need to write the equilibrium constant, write the formula for that. And again, it's the concentration of product over the concentration of reactant. Here the products are Cn minus and H3O plus. So you will multiply them on top of the equilibrium constant expression. So they are not raised to any power because their coefficient are 1 for both of them. Over the concentration of the reactant, and here again water is a liquid and is not included in the equilibrium constant, so it's only HCN, the concentration of HCN in the denominator. Next, you plug in the values for each concentration, and so Cn minus and H3O plus have the same value, 4.9 10 to the negative 5 times 4.9 10 to the negative 5 over the concentration of HCN is 5. You do this on your calculator. So using the TI30X2S calculator, you do 4.9 second EE key minus 5 and times 4.9 second EE key minus 5 divided by 5. And sorry, I should have done that earlier. Times 4.9 divided by 5. The calculator answer is 4.802. 4.802 times 10 to the 10. So here you have to think about sig figs as always. And the concentration of the hydrocyanic acid is 5. And it's only 1 digit, 1 sig fig. So you need to keep 1 sig fig. So the 4.802 will be rounded to 5 because you keep the 4, but what comes after is an 8. So you round up. And so it's 5 times 10 to the negative 10. We didn't say that earlier, but there is no unit for K. K is a unitless value. Sorry. So now we need to decide if we have a strong acid or a weak acid. And earlier we learned that the stronger the acid, the larger the Ka value. So here, 5, 10 to the negative 10 is a very small value, right? When you have a negative exponent, it's like dividing 5 10 times by 10. So that's a very small number. So our Ka value is very, very small. So it's the contrary of being large, which means we have a weak acid. So the Ka is very, very small. So the equilibrium is favoring the reactant because we have a weak acid, right? And it's mostly undissociated. If you look at the Ka expression, you can retrieve that. If you look that it's the hydronium ion concentration times the cyanide ion over the HCN concentration. If it's a very small value, you can see that means your numerator is small and your denominator is large. And that confirms that you have a weak acid because it means it's mostly, the equilibrium is mostly to the left, which means you have a lot of undissociated acid, HCN, which is neutral and makes it a weak electrolyte. And so a weak electrolyte is a weak acid. You can also verify that by looking at the concentrations. If you look at the concentration of HCN, it's 5 molar. It's a very large value compared to the cyanide ion and the hydronium ion. They both have 4.9 10 to the negative 5. 10 to the negative 5 is a small value, right? So that confirms that on the right side you have small concentrations and on the left side of the arrow you have a large concentration. And so your acid is not dissociating very much and it's a weak acid. So as we said, water is an amphoteric substance, which means it can act as both an acid and a base. And so you can then make 2 water molecules react together in an acid-base reaction. And so this is showing in this reaction. On the left side, you have 1 molecule of water. That first molecule will be the one that will act as an acid. And then a second molecule of water, and this one will act as a base. When the molecule of water acts as an acid, it's donating an H+, and so H2O, when it donates an H+, it becomes OH-, right? Because the one of the bond becomes a lone pair, and that makes it a negative charge on the OH-. And so OH- to the right of the arrows here is the conjugate base of water as an acid. The other molecule of water acting as a base will accept the proton. And so one of the lone pair will become a bond with another hydrogen. And that's going to be the H3O plus to the right. The proton comes with a positive charge, so that's why it's positively charged. And this H3O plus is the hydronium ion, and that's the conjugate acid to the base, to water as a base. So if we write the equilibrium constant for this equation, again, it's the concentration of the reactant over the concentration of the product. And so here, let's call it Kw. Kw is concentration of product, which means H3O plus times OH minus. They have no exponent because their coefficients are 1. Over the concentration of reactant, but here you can see that on the reactant side, we only have 2 molecules of water, which is our solvent here, or liquid. So as a liquid, it's not included in the K value. So then the Kw will stay as concentration of the hydronium ion times concentration of the hydroxide ion. This Kw can be calculated and has been calculated at room temperature. It has been found that the concentration of H3O plus equals the concentration of OH minus equals 1.010 to the negative 7 molar. The reason why these two concentrations are equal, it's because you can see that when water dissociates, you make both ions at the same time. You cannot make one without making the other. So that's why those concentrations have been found equal in pure water, and they have been found to be equal to 1.07 10 to the negative 7. 1.01 10 to the negative 7 molar. So if we plug in the value into the Kw expression, it will become Kw equals 1 10 to the negative 7 times 1 10 to the negative 7, which is equal to 1.0 times 10 to the negative 14. When you multiply two numbers with the numbers of the same kind with exponent, the exponent are added. So 7 plus 7 or minus 7 plus minus 7 equals minus 14. Remember how the equilibrium constants have no unit. So this is staying as is. And so Kw is a constant. It's always equal to 1 10 to the negative 14 for all aqueous solutions at 25 degrees, not just pure water. It happens that all aqueous solutions have this value staying true. And so it's only in water that, pure water, that the hydronium ion concentration equals the OH minus concentration. But in most solutions, they are not equal, but their product, the product of their concentration stays equal to 1.0 10 to the negative 14. This Kw is called the ion product constant for water. And it's found in your yellow packet. If you go back to page 5, the ion product constant of water, you can find it in the middle right. It's given to you because it's used to do some calculations of concentration. So, as I said, all aqueous solutions contain those ions, the hydronium ion and the hydroxide ion. And so depending on which one exceeds in number or the other, you will classify the solutions as acidic, neutral, or basic. Let's start with when the concentrations are equal, when the hydronium ion concentration is equal to the hydroxide ion concentration. When they are equal, they are necessarily equal to 1 10 to the negative 7 molar. The one here is implied. It's 10 to the negative 7, but it's 1 times 10 to the negative 7 molar. When you are in this case, when you have reached these conditions, then it's a neutral solution. It has to be exactly equal. Whenever you deviate from those concentrations being equal, you will get either an acidic solution or a basic solution. let's look first to the left. If the hydronium ion concentration is larger, which means greater than 10 to the negative 7, so hydronium ion concentration greater than 1 10 to the negative 7 molar, then the hydroxide ion concentration will necessarily be lower, smaller, so that their product is still equal to the Kw. And so when one increases, the other has to decrease. And when it's the hydronium ion concentration that is larger in value, then we call that an acidic solution. So on the left, you have an illustration of what is an acidic solution. Now, if on the contrary, you have the hydroxide ion concentration being larger than the hydronium ion concentration, which means the hydronium ion concentration is less than 1 10 to the negative 7 molar, whenever it's under that value, you have a basic solution. And again, if the hydronium ion concentration is small, then the hydroxide ion concentration will be large to compensate, so that their product, when you multiply those two concentrations together, you still get the Kw value. So you need to remember these classifications of the solutions, that whenever the hydronium ion concentration is larger than 1 10 to the negative 7 molar, it's an acidic solution. When the hydronium and hydroxide ion concentrations are both equal to 1 10 to the negative 7 molar, it's a neutral solution. And when the hydronium ion concentration is less than 1 10 to the negative 7 molar, it's a basic solution. This you have to remember, it's not in your yellow packet. So remember that. So this Kw expression is often used to calculate concentration of either the hydronium ion concentration or the hydroxide ion concentration. So let's look at, for example, if you know the hydronium ion concentration and you want to calculate the hydroxide ion concentration. So you will use this Kw formula. And because we know Kw, it's always that 1 10 to the negative 14 value. We know H3O plus in this case, and we want to find OH minus. So we need to solve for OH minus. To isolate OH minus, you need to divide both sides of the equal sign by H3O plus. And so you can see that on the right side of this equal sign, if you divide by H3O plus, both H3O plus cancel, and you're left with just OH minus, and that will be equal to Kw over H3O plus. Kw has a known value of 1.0 times 10 to the negative 14. And so when you want to calculate your hydroxide ion concentration, you plug in your hydronium ion concentration in the denominator, and that will give you your hydroxide ion concentration. If now, on the contrary, you know the hydroxide ion concentration and you want to calculate the hydronium ion concentration, again, you start from the Kw formula. This time we know Kw and OH minus. We want to get rid of H3O plus on the right side of the equal sign. So for this, no, sorry, we want to get rid of the OH minus, excuse me. We want to get rid of the OH minus because we want to calculate H3O plus. So we will divide both sides by OH minus. If you divide both sides by OH minus, you can see that OH minus cancels on the right side, and you're left with H3O plus equals, and then the other side will have Kw over OH minus. Knowing the value of Kw is 1 10 to the negative 14, that's the formula you would use. And so you can see they are very similar. So if you are not so sure about how to get back to these formulas, what you need to remember is that the Kw will always be in the numerator, and then if one concentration is on one side, then the other will be on the other side in the denominator. It's always in that configuration. So let's check your learning by doing practice problem number 7 and 8. So practice problem 7 and 8. So you can pause now before getting to the answer of practice problem 7. That problem is asking for the hydroxide ion concentration if the concentration of H3O plus in a cup of coffee is 1.0 times 10 to the negative 5 molar. And after that, after you've calculated that value, decide if your coffee is acidic or basic. So we have seen that to get the concentration of the hydroxide ion, we need to use the Kw expression, divide both sides by H3O plus, and then we have OH minus by itself on the left side of the equal sign, equals Kw over H3O plus. Kw is 1.010 to the negative 14. You plug in the value for the hydronium ion, and that's 1.010 to the negative 5. Do that in your calculator, and if you use the EE key, as I taught you, you should not make any mistake and get 1 times 10 to the negative 9. The way to verify that, if you're at ease with numbers raised to an exponent, here it's 10 to the negative 14 over 10 to the negative 5. If you move 10 to the negative 5 to the numerator, it changes its exponent to positive 5. So it's 10 to the negative 14 times 10 to the negative 5. When you multiply numbers that have exponent like that, same numbers that have an exponent, you add the exponent. So negative 14 plus 5 makes negative 9. So you could verify that value mentally also, if you're at ease with this kind of calculation. So here, even though Kw is unitless, the concentrations do have units. And when you are asked to calculate the concentration, you need to add capital M for molarity, right? The hydroxide ion concentration is 1.010 to the negative 9 molar. And we keep 2 sig figs because we had 2 sig figs in both values. Now, is this acidic or basic? If you look at the concentration of OH minus, it's 110 to the negative 9, and the H3O plus, it's 110 to the negative minus 5. 110 to the negative 5 is a larger value than 110 to the negative 9, because 110 to the negative 9 means you divide 9 times by 10. 110 to the negative 5 means you divide 5 times by 10. So that's a smaller, that's a larger value than 110 to the negative 9. So the concentration of H3O plus is larger than the concentration of OH minus. Even though both values are very small, the H3O plus is still much larger than the OH minus. If we have more H3O plus, you can associate H3O plus with acids, and that tells you it's an acidic solution. So yes, coffee is acidic overall. Practice problem 8, which is a continuation of practice problem 6. It gives you the concentrations of HCN, CN minus, and then the hydronium ion. And you have the equation. There is extra information in this problem, right? When you are asked to calculate the concentration of the hydroxide ion, OH minus, you don't need all of this. You only need H3O plus, right? So the way to solve this is to, again, take the KW formula, because when you have questions asking for a hydroxide ion concentration and you're given the hydronium ion concentration, you want to use the KW formula. Here, it will be OH minus that you want to isolate. Divide both sides of this equation by H3O plus, and you get OH minus by itself, and it's equal to KW over H3O plus. Next, you plug in the values, and KW is 1.0 times 10 to the negative 14 over the concentration of H3O plus. Plug in the value of H3O plus, and it's 4.9 times 10 to the negative 5. So do that in your calculator. And again, if you use the EE key, the calculator will know that the times 10 to the negative 5 belongs to the 4.9. If you don't use the EE key and do times 10 power, your calculator might move the times 10 to the negative 5 to the numerator, and that will give you, so let me calculate that. That would, well, that would be giving you, yeah, hold on. So if you are not using the EE key, and that your calculator moves the 10 to the negative 5 to the numerator, because, for example, you haven't used the parentheses, the calculator answer will be 2.0408 times 10 to the negative 20. If you get that, you know that you need to use the EE key so that your calculator knows to keep the coefficient with the power of 10. So the calculator answer is 2.0408 times 10 to the negative 10. We have 2 sig figs on the numerator, 2 sig figs in the denominator, so we keep 2 sig figs, and so we run to 2.0 times 10 to the negative 10, and don't forget to add the unit of capital M for molarity. So we need to decide if it's acidic or basic formula, and again, you look at the hydroxide ion concentration. It's 2.0 times 10 to the negative 10, which is a very small value, but the hydronium ion concentration is 4.9 10 to the negative 5. 10 to the negative 5 is a larger value than 10 to the negative 10. So again, we have more H3O plus ions than OH minus ions. And so because of that, it's going to be acidic, right? When your hydronium ion concentration is larger than your hydroxide ion concentration, it's an acidic solution.